Hi everyone, my name is Javier. I'm part of the research staff at the Neuromuscular Mechanics Lab here at Simon Fraser University. And today we're going to be talking about one of the main piece of work from my thesis, which is Flexodeal, which is a computational framework for musculoskeletal simulation. So happy you can join us. There's not a lot of math here. There's just one slide with math. So I'm going to go a bit of introduction to software itself, the background, and then we're going to jump right away, starting downloading stuff and looking at some code, okay? So let's see. And by the way, these slides are available in my GitHub. So there should be a Flexodeal tutorials repo. So down the road, when we start to change between the presentation and the Visual Studio window, it might be useful for you to have them in the back so that you can go back and forth, right? Again, just go to my GitHub, Flexodeal tutorials. There's a PDF and there's a PowerPoint version. So what is Flexodeal? Flexodeal, as you may or may not know, it's a computational framework that has been developed here at the lab to simulate the dynamic deformation of active muscle tissue in 3 dimensions based on commonly accepted physiological principles. So there's quite a few keywords here. First of all, computational framework. So we're going to be talking exclusively about in silico experiments. Dynamic deformation, meaning that we include the effects of velocity. That's included in the model, but it's optional. There are also quasi-static simulations where you don't use the effects of velocity. That's up to you. Active muscle tissue, so it's not just passive tissue, you can activate it. And it's based on commonly accepted physiological principles, the main one of them being Hill's model. All right. It is written in C++. It's powered by the DL2 library. But DL2 is a finite element library, not just used for this software, but there's many other applications in computational mechanics, solid mechanics, fluid mechanics, right? And because it's a finite element library, well, this classification is based on finite elements. And the geometries are meshed using hexahedral elements or voxels, right? I might refer to voxels at some point. And I just have a representative figure here. Yes. What do we have here? Basically, this is just a cartoon of the things that you can do here. Basically, you have 2 profiles of strain and activation. So muscle strain, or you can think of it as muscle length. You're controlling the length of the muscle. At the same time, you have an activation profile. Both are going at the same time, and then the muscle responds in an appropriate way, right? And we'll get to this example eventually in tutorial 2. Now, very briefly, this framework is based on continuum mechanics, right? So you're going to have a solid that is going to have some kind of deformation, where the main ingredient is your deformation tensor F, which is the gradient of this deformation mapping, right? And that is the one that is applied to the fibers themselves, right? So we have a solid that is a composite of base material and fibers, right? So whenever the solid gets deformed, so do the fibers. They get stretched, their pennation angle can change. So everything is interconnected. It's based on a 3-field formulation. And the stress, as I was saying, this model has the additive response of several components. So the main one being Hill's model, so the along fiber component, a base material component, intramuscular fat, tendon, and aponeurosis. That would be the whole model, right? Now, it comes in 2 versions. There's Flexodeal Lite and just Flexodeal. We're going to focus on Flexodeal Lite today, and then tutorial 2 will be about Flexodeal. Now, what's the difference between the 2 of them? In essence, they both have the same muscle model. Their difference lies mostly in the purpose of these 2 pieces of code. Flexodeal Lite is a simpler code that is suitable for numerical developments or simple experiments, right? And by numerical developments, I mean anything that is related to like the linear solvers or the nonlinear solves, all the numerical algorithms behind, right? And it's a simpler code that is meant to run a little bit faster just because there's less lines of codes. The model is also simpler in this case because we only have muscle tissue, so no tendon and aponeurosis in Flexodeal Lite. It's a fat-free muscle by default, but soon we will be adding some intramuscular fat to that. And the default geometry is just a cuboid, right? Something very simple. So you can think of it as like a little biopsy of muscle tissue, right? No more than that. Then we have Flexodeal, which is going to be the focus of the next tutorial. So it's a more complex code suitable for more realistic experiments because now you have access to all parts of muscle. So muscle tissue, tendon, aponeurosis, and also intramuscular fat. You can also define custom fiber orientations, right? You can also do them in Flexodeal Lite, of course, but those are uniform. It's the same fiber orientations throughout. But in Flexodeal, you can customize them. You can have maybe even like a bipennate muscle, right? By default, we have this geometry here that was used in this paper from 2021. And then there we have muscle tissue and 2 layers of aponeurosis. So like we get a little bit more realistic. So let's begin writing some lines of code. So the first thing is to download and compile Flexodeal Lite. If you've done this already, you can just go back to your folder where you had it. If not, you can do it now. Basically, what we're going to do here is to download the latest release of Flexodeal. So I'm just going to open this link here. So there's several releases. Every time we add something new to Flexodeal Lite, we put out a new release. So we're going to use the latest one, version 161. And at home you can read through like the release notes just to see how the software has evolved in this past couple of years. So that's what I'm going to do now. Question: is anyone using the lab computers, like as a headless server? No. Okay.
Do you want something to run with the access?
No, it's just to because that means if you're running on the Linux machine, you don't have like a GUI, so you'll probably have to use the command line, right? So I'm going to download Flexodeal. Just going to download the zip code here. And in my case, it's just my downloads folder here. So I'm just going to move this to some other folder. I mean, in my case, let me just go here. I'm just choosing a folder where to put this this version of Flexodeal Sandbox. Just to not mix it up with other things that I have, right? It doesn't matter where you leave it. All right, so we've downloaded that. In my case, it was unzipped immediately. If not, called out, just right-click, unzip. Then we can go to the Flexodeal folder and start compiling as follows. So I'm using a Mac. There's plenty of alternatives to do this. You can open Visual Studio right away or your terminal. I use iTerm, but there's also like any terminal works, right? If you're on Windows, you can use PowerShell, it's fine. So when you just download Flexodeal, there's 3 steps, right? First one being, actually there's mainly 2 steps. The first one is calling CMake. CMake is, so to speak, the platform that links Flexodeal with DL2, wherever you have your DL2 installed. Right, so that's what I'm gonna do now. I'm going to navigate to this folder that I just created. In my case, it was something like Dropbox view. I forgot where I left this. Out 01. There you go. Again, we go to wherever you downloaded your Flexodeal folder. And here's where I'm going to call cmake, right? So cmake dot. So basically cmake dot, that is referring to the cmake list file that I have there in that folder, like in the current directory. And the following flags, we'll type release. You also use debug, the flag debug. If you're modifying the C++ code, of course, that's going to run much slower. But that means that you can also debug it with other tools like GDB, right? But we don't need that now. We just do it in release. And then the directory where DL2 is. Now, depending on how you install DL2, you may or may not need this flag because depending on the way you install it, sometimes you can create an environment variable is created with the location of DL2, right? And this is also the case if you're working on a cluster. Typically, we don't know where these libraries are installed, but there's a flag already in the system. So you don't have to include this DL2 there flag, right? In my case, it's something like that. But again, it depends on where you installed it, depends on your machine. So we have some outputs here. It says that it was built on release mode. So now I have even more files. And then I just make the software. There we go. So just typically it takes a couple of seconds. Shouldn't take more than a minute, I would say, or even more than 30 seconds. So now I have my executable Flexodeal Lite. That's the one I'm going to be calling throughout this tutorial, right? Any questions so far? Are we all on the same page? Everything compiled nicely? Okay, good. That's great. If at any point your software just doesn't compile or breaks down, you're like, let me know and we can look at it, right? So at this point, we can just let Flexodeal Lite run in the background with the default experiment because that's what we're going to talk about next. It's going to take a couple of seconds or minutes depending on your machine. So I'm just going to run it. And we will go about those outputs in the next tutorial probably. So for now, don't worry too much about it. I'm just going to minimize this and let it run in the background. So in running that command, we're basically running the default experiment. It's computing some stuff in the background. We're going to go over that because with that default experiment, I can tell you what are the main components that you need in setting pretty much any experiment, any computational experiment with Flexodeal. So in the Flexodeal framework, we follow the principles of computational mechanics. If you've done computational mechanics before, you can start imagining that you need a mesh, you need some parameters, you need to define your model. So we're going to do all of that. And in addition, we need to define an activation profile, right? Particular for this model. And again, when you run just Flexodeal Lite, no arguments, nothing else, you're running the default experiment. So the first one is a geometry or a computational domain, right? So again, Flexodeal Lite by default is just a cuboid. So it's just muscle block, muscle tissue, no aponeurosis or tendon. And here's a brief description of the geometry. So it's going to be given by a muscle length, muscle height, and muscle width, right? So 3D again. The fiber orientation is simply just cosine of the pronation angle and then sine of the pronation angle. So we're going to have X and Z components. So all my fibers will be oriented on the XZ plane. L here, or L hat, would be the line of action. Now the line of action is it's set to be the x-axis for now. Eventually in future versions of Flexodeal we might modify that. But for now it's set to the x-axis, meaning that you better orient your meshes to align with that line of action, right? And we also need to be aware of the boundary ADs, right? So we're going to have this geometry, and then it comes with this boundary ADs. So on the left side, it's going to be ID 0, right side, ID 1. The left side is a fixed boundary. There's no displacement there. So, or we have a zero Dirichlet condition. And then on ID 1, we're going to have a moving boundary. So that's going to be where we're going to prescribe the strain. All the other faces, so 2, 3, 4, and 5, the other 4 faces of this cuboid, they're all traction free, right? So they're free to deform without resistance, basically. So that's the main thing with respect to the geometry. Any questions about this? Does this make sense? I think it's important that when you're creating your geometry, however you create it, you are always aware of your boundary ADs, because I feel like that's the first source of error, right? Sometimes we forget about what the boundary ADs are, and then we don't understand what the code is doing. And it's because we simply didn't set up the boundary conditions properly, right? Maybe we set them somewhere else, right? So always be aware of your boundary ADs. Now, we're also going to have a parameters file. It's a file with an extension PRM that contains several model and simulation parameters. So model parameters strictly related to the muscle model, simulation parameters more like on the sort of like numerical aspects of it. There's a lot of them, but some of the most important ones I would say. First is the type of simulation, whether you want a dynamic or quasi-static simulation. So in a dynamic simulation, you include velocity effects. In a quasi-static, you don't. And you also don't include the effects of mass. Simulation time and time step size, right? In the examples that we're going to run today, they will all converge, it will all work. But sometimes if your code is crashing, maybe it's because you set up a time step size that was too big, right? So you'll have to modify that. Muscle block dimensions, you can scale this block however you like. Fiber orientations, the way we described them before. Markers, so we're going to talk a little bit about markers. These are used to track point displacements. Again, we're going to talk more about that in a bit. The solver type that you're using, typically we use a direct solver for coarse meshes because that's a smaller problem. And then CG, which stands for conjugate gradient. It's another mathematical method to solve linear systems of equations. If you have finer meshes and a much larger problem to solve, then you might be better using conjugate gradient. So let's open this file. And for this, I'm just going to go to basically what I do always when I'm working with Flexodeal. I open a Visual Studio window, and then I open the folder, right? So I'm just going to navigate where I store my this version of Flexodeal. So somewhere around here. So yeah, here you have your Visual Studio window, and we'll have a look at all these files here. So the parameters file, we have it here. Again, it's a long list of parameters. you're not going to modify all of them all the time. Like I said, this one you're most likely to modify, dynamic or quasi-static, maybe your polynomial degree, maybe your refinement level, so how fine your mesh is. The higher the number, the finer it is. Muscle block dimensions, if you want to scale your grid, but just the grid, nothing else. But you can also scale your grid beforehand. Some parameters related to the linear solvers. So basically, once your mathematical model, your PDEs are converted into linear systems of equations, well, how do you solve them, right? You have a bunch of parameters here. Like I said, this is probably the one that you're gonna modify the most. Maybe the preconditioner. If you see that your solvers are taking too long, your linear solves, then maybe you can try a different preconditioner. Then we have a material section. We define the muscle density, the maximum isometric stress, bulk modulus, like all these quantities. The maximum fiber strain rate, typically we set it to 5 for slow fibers, 10 for fast fibers. Fiber orientation, this is just, I believe in this case is 30 degrees, so first component would be cosine of 30 degrees, and then the last component would be sine of 30 degrees. Then some base material properties. You can even modify the constants that we use in the strain energy function for the base material, but typically we don't. The one parameter that you might want to modify is the base material factor. But again, it all depends on your experiment, right? Typically, if you're not seeing convergence right away, if your model is just not running, one option is to increase this factor, say, to 1.5, right? And see what happens. We would like to always leave it at 1, but sometimes that might not be feasible, right? And again, it depends a lot on, it depends, it's on a case-by-case basis, basically, right? If you can leave it at 1, great. If not, you can explore other options. So for the non-linear solver here, you can increase or decrease your tolerance. I mean, these are at least the displacement tolerance is in terms of meters. So you have to think basically how much of resolution do you want to achieve? Do you really want to achieve millimetric or micrometric resolution? Depends on the dimensions of your problem, right? If you have a very, very tiny muscle, maybe that's a tolerance that is too large. But if you have, say, like a human-sized muscle or larger, then that's probably enough, right? Then you have the time section, which is probably the section that you're going to modify the most, because it has two simple things: the end time of simulation and then the time step size. And this is something that at some point me or someone else will fix, because basically we always want to capture the very last time step. So one quick to do that is to add a very small number to your simulation end time, right? But again, in a future version of Flexodeal, we're going to fix that nuance. There's a section called prescribed displacement here that all it does is set the quote-unquote pulling phase ID, basically your ID that is bound to move, right? Now, if we're talking about an isometric contraction and your boundary doesn't move, you're not prescribing a strain there, that's the ID that will be used to report a time series of forces. So it's important to keep track also of that ID, even if you're not prescribing a non-zero strain, right? Then we set the file for the markers. Again, I'm gonna talk a little bit in just a couple of slides. But here we set the file name, so it's called markers.dat. It's like right there. And then we have a section about binary files. So if you need very detailed information about most of like the tensors, quadrature points, and deformation tensors, and your main unknown variables, so displacement, pressure, dilatation. If you really need that detailed information, like at every quadrature point and in the in the geometry, you can do so. You can export that or like that fine data, because we're gonna see how like we can view some files in ParaView, right? But that gives you a view. You can do some things with ParaView, but if you need finer information, you can export these files. But just to let you know, they're binary, so you're not gonna be able to read them right away. You have to pre-process them in Python or MATLAB. And they tend to be very heavy, so that's why they're turned off by default. But if you need it, just change this by true, and then you'll get it. Any questions about this parameters file? I know that it's a lot to digest, because again, there's a lot of parameters, and if you really want to know what each one of them means, you have to go to like basically the equations. And that can take a lot of time. But the main idea here is for you to understand what are the things that you can modify here. Now, the next thing that you want to set up are boundary strain and activation files. And the way we do this is as follows. So we're going to have a time-dependent prescribed boundary strain at that phase ID that we set in the parameters file, which is by default 1. And the time-dependent activation profile. How do we implement this? It's very simple. So for the first row, I'm going to have my strain profile. Basically, what I want to do here is to first stretch my muscle 10%, hold it for some time, and then shorten it to like 0.9 of like the initial muscle length. So that's why your strain is minus 0.1, right? That's all I want to do. Now, how is it evaluated inside like Flexodeal? Basically, it's linear interpolation. So if you want to create a more complicated profile, say like that one, then you're gonna need more points. That's all. And the file is very simple. It's a table of coordinated pairs, basically. First column is time, second column is strain. You can generate that with Python, MATLAB, Excel, many options there. And then the activation is the same thing. So what I want to do in this experiment is to basically lengthen the muscle block until 1.1 times its initial length, and then activate it, right? Start at 0.1 seconds, over a span of 0.2 seconds, till I reach maximal activation, then just hold it there, active. So then my file is very simple. Again, just these 4 points that define the curve. And that's about it. Again, if you need more complicated strain or activation profiles, you just add more points, right? And then Flexodeal will read them by linear interpolation. Any questions about this?
Yeah, so these .dat files, are they just tab separated value files?
They're space separated.
They're space separated.
Yeah, space separated. Now, if by any reason you do them tab separated, there's a reason that they will be read too.
Right.
Not so much if they're comma separated. Yeah. So then we're gonna have the markers, right? The idea of the markers is basically have some point displacements to track. Maybe you have a block of muscle, you want to track your displacement at 3 particular points, right? You will have a displacement field, a 3D displacement field to look at. But maybe you're just interested in like 3 particular points, or you want to report them separately, right? So it's a quick way to do that. Now, the caveat is that these markers must correspond to mesh vertices. They have to, right? Because the way finite elements are set. So basically the displacement field has degrees of freedom at mesh vertices. So that's the only place where we truly know the displacement. Of course, that requires you to have your mesh, visualize it. So maybe that's hard to do sometimes. If you do not require that feature immediately, like you can just use an empty file, it's fine. And again, very simple, space separated. There's 4 columns here. The first one is just a name to identify the marker, and then the X, Y, and Z components of that point. No more than that. And finally some notes. So CMake compile a machine-dependent version of Flexodeal, meaning that if you, for any reason, actually I do this a lot, like I compile versions of Flexodeal like in my Dropbox so that I can read the output somewhere else, especially like if I'm going between different machines, right? Know that if you compile Flexodeal in one machine, you might not be able to run in a different one, right? And unless you modify the C++ file, so the .cc file, you don't need to call make or CMake every time you run Flexodeal Lite, right? And if the call to Flexodeal Lite itself accepts 4 parameters. If you run it without any parameters, like what we did earlier, those are the values by default. So, can talk about output files. And for that, I'm just going to go back to my I can go back to my terminal here. Hopefully it's done. Is anyone's code still running? I hope not. Should be a relatively short code. In my machine, it took a bit over 2 minutes. So now we can look at the files that we have available here. For this, I'm just going to go back to my Visual Studio Code, because this is the output folder. By default, it's just today's date and time, and some flags. So basically, you see that we have a bunch of CSV files and a bunch of VTU files. CSV files, you can quickly open them like either here. Sometimes you just open them here, or you can also open them in Excel and start plotting things. That's up to you. Now, what are these files? In terms of CSV files, we're going to have time series for activation and muscle length, the displacements at these markers that I define, energies, because these are all integrated quantities, so they're just time dependent. Force, and this is probably one of the most important CSV files, in my opinion, the time series of force at the moving end of the muscle. So in that pulling ID that we set in the parameters file, in the direction of the line of action. Many times that is the one component that we're interested in, right? So we spot them separately. But also, we can also output the vectorial force at each boundary ID and at each time step. Now for that, you're gonna have a series of CSV files at each time step, right? And then you can post-process that however you like, right? That's the idea. We're going to have some velocity averages. They're all going to be in this gearing info or information file, and also mean stretch and mean pennation angle. And then in terms of parity files, actually this should be like .vto. These are all .vto files, .csv. Main model unknowns: muscle displacement, pressure and dilatation, velocity, fiber stretch, fiber orientations, fiber strain rate, and the Kirchhoff stress sensor, in case you're interested in that. So let's go back to the files we had, and let's open ParaView. Now, I'm not going to do a whole tutorial on ParaView because there's a lot that you can do there, but I strongly suggest you to look for even YouTube tutorials or documentation for ParaView, because really it's a really powerful software. So I'm going to open this file. And just navigate to the folder I just created. Channel 1. There we go. So that's the folder that was just created. And I have a bunch of files here. Again, I'm not going to do a whole tutorial on ParaView, but perhaps one of the things that I always like to remind people of is that if you just play this, right? Color-wise, it's odd at first, and what I recommend people to do is always to rescale to data range over all time steps. So the button that is like right there. Because if for some reason the color scale is always set to like, I don't know if it is like the first time step or the last time step, right? So if anything goes out of range, then the colors won't make sense, right? So again, in the default experiment, I'm lengthening my muscle block, activating it, then shortening it. So first lengthens, then it's activated, fibers rotate, and then we shorten it. And we can quickly have a look at the mesh that we used here. A mesh, by the way, that is generated automatically by DL2, right? So you're gonna have different fields. Again, you can have a deeper look at this on your own, but perhaps one of the files that I like the most is this one about stretch, because you have the orientation field. So again, I'm gonna rescale to all data steps. Now, the deformation is the same. And this is the orientation magnitude. So at each point in your domain, basically, you're gonna have a fiber orientation vector, right? Now that vector, as it is here, doesn't have unit magnitude. The magnitude of that vector is precisely the fiber stretch. You also have a fiber stretch here field to verify that. Now, why is, in my opinion, important? It's because when you want to plot fiber orientations, maybe you want to plot the fibers themselves, right? So I'm going to do one quick thing here, just to create a glyph of this orientation field. So then your fiber orientations vary, right? That's one way of viewing things, right? Or you can use the streamlines to sort of like render some fibers, right? And for that, I'm just gonna set some extra parameters here. Let me see if I can do this quickly. So when I want to plot these streamlines, right? Well, I'm gonna use the orientation, where is it? Here. The orientation field, and then scale them. Where's the, sorry, this one. This one, the stream tracer. Just gonna do it as a sphere here. Let's leave it at 15. Maybe do like 1,000 points. Let's see. Seems like we hit a little bug here. Anyways, I'm not going to spend much time on this, but for the moment you can do the glyph, and then we'll double check we can check the orientations maybe in the next tutorial, right? Just to create this the streamlines, because there's a little bit of some more parameters that you have to play with. Sometimes you have to play with the number of seeds and even the numerical methods that you're using to compute them. So we can go a lot more deep into it, but you can do it. Now, 16. So any questions about these files? I know there's a lot to unpack here. We only have 1 hour, so Again, you can, on your own, you can explore any of these files, create glyphs and all sorts of visualizations. Now, let's run some simple experiments. These experiments are all coded already, so we're just running them. We're going to briefly look at the files, and then we'll get some time for you to try something, okay? So the first one is perhaps the simplest, yet the most important example, which is an isometric contraction in this muscle block. To run that, I'm going to open a terminal here. So I have my terminal down there. I have my executable there. And you can see that there's a folder with examples already. So those are the parameters that I'm going to use. So to run this isometric contraction, I'm going to use the following parameters. ic_parameters.prm. Boundary strain, well, samples ic strain.dat. Activation, examples activation.dat. And let's give it another name for my output directory. Let's call it, I don't know, results IC. So 4 parameters, and I'm referring to these files here that are inside the examples folder. And then you can click enter and something will run. So, all good? So I'm just gonna run this. And again, don't worry much about the terminal output here. We'll go over that in the next tutorial. Basically what I'm doing here is an isometric contraction, so both ends of my muscle blocks are fixed. The block doesn't have any pination. It's just parallel fiber. And I'm going to fully activate the block of muscle over a span of 1 second. That's about it, and in just 10 time steps. If you go to the parameters file for this experiment, it is quasi-static. As you can see right there, it's not dynamic, it's just an isometric contraction. We don't need velocity here. Though you could run a dynamic contraction if you want to. You have the option. But this is an important experiment because it's one of the few experiments where we know what the force is going to be at the end of the muscle, right? Because we know what the cross-sectional area is. We know what the maximum isometric stress is. So we know that at the ends of the muscle, we should expect a force of about 20 newtons. And if I go back to my terminal, it should be done by now or nearly done. Very briefly, in this table here, I have forces, right? I report the forces at each boundary AD. And you can see that at boundary 0 and 1, the total force is about 20 newtons, right? So if you're modifying the code or you're doing any other modification, this is one thing that you can try. If you get something close to 20 newtons, not exactly 20, but close to 20, you're good to go. If not, that means that there's a bug in your code that you have to fix. I'm gonna skip the visualization because again, it's just a block of muscle. It will bulge. That's all it does, right? You can also set a contraction on the ascending limb of the first curve here. So on the left side, on the blue side here, which you can run using those parameters. We can consider the same muscle block and also a dynamic experiment with this strain and activation profile. So basically, shorten the muscle, 25% over 2 seconds, then activate it over the next second, so 3 seconds, up to here, hold it there for some time, and then lengthen it back to its initial length. That's all we want to do. And those examples are also here. So activation, again, So for the activation, I need 1, 2, 3, 4 points. Those are the 4 points that are defined there. For the boundary strain, I need 1, 2, 3, 4 points as well. So 4 points. At 2 seconds, the strain is minus 0.25. At 5 seconds, it's also minus 0.25. And then at 7 seconds, the strain is 0 again. And then you can run the same thing. Let me go squiggly here. So parameters, so examples, and then ascending limb, .prm, boundary strain, strain.dat, activation, output there, results, the ascending limb. Now if I didn't mess up any parameters, then this should run also in about 30 seconds or so. So while that runs, well, you can try to do one yourself. Now on the descending limb. So for that, you can lengthen the muscle block to 1.1 times its initial length over 2 seconds, then perform an isometric contraction over 1 second, and then shorten. So I encourage you to try it out on your own the first couple of minutes, basically to get you started faster. You can copy these 3 files, the activation parameters and strain files, just give them another name, and then you can start modifying those. For the parameters files, the only thing that you'd have to modify is the end time, simulation end time, nothing else. And of course, if you have any questions, let me know. So I'll give you a couple of minutes, and then I'll do it at the end.
I had a question.
Yes.
About the P2P0.
Mm-hmm.
We should put it here, as I say, 0.
So sorry, the what?
P over P0.
Ah, yeah.
And
We're not using.
I know that there is some other option than 0.
Yeah, that is one parameter that we left. We left in the parameters file, but we're not using it yet.
Yeah,
but
later we will talk about it.
Yeah, I mean, well, it's not implemented basically yet, because that's something that we have to implement rather soon. Yeah.
But there is some other options instead of pure to P2 over P0 than 0.
Yeah, I mean, you can modify it to any value, but at this point it will have no effect, because basically the traction condition is we still haven't implemented that yet.
In both.
In both versions, yeah. So right now you can control your muscle length, but say it's not like you can prescribe a force at the end of the muscle, or a pressure in this case, right? Which is what that parameter is used for.
Yeah.
Yeah. We're just working on that.
Yeah. So when we just implement our code for putting the pressure on it, when we define our pressure in under boundary condition, it would be applied.
Yeah, exactly.
Okay.
But yeah, the other day I was actually I started working on that, and yeah, so I think it will come out in the next couple of weeks. I think after these tutorials. Yeah. So I'm just gonna start creating like the files that we need for this experiment. Strain. Then I'm just going to copy this file here. Stop here. All right. So just copy my parameters file. My contraction happens over 5 seconds total, so I'm just gonna set that to 5. So for activation, I'm passively lengthening my muscle block over the first 2 seconds. So I start with 0 activation. At 2 seconds, I'm still at 0 activation. Then over 1 second, so at 3 seconds, I'm gonna have just 50% activation. And I'm gonna shorten the muscle back to its initial length over 2 seconds, but I'm gonna keep it active, right? So just that. Now for the strain, I start at its initial length. Over 2 seconds, I stretch it, I lengthen it 10%. Then I activate over 1 second, so I'm gonna hold it. So at 3 seconds, that's gonna be still 0.1. And then over 2 seconds, I'm gonna shorten it back to its initial length. And then I'm just gonna, I was in the examples folder here, so I'm just gonna go back. So examples, PRM, boundary strain, samples, strain. I just move this here. Activation. Samples. Actually, results descendingly. So the parameters, the strain, and then the activation. Then it's gonna do some things here. And just so you know, especially for the people online, we are going to be done in the next 5 minutes, right? So, simulation's done. Go back to Power View. I'm gonna just remove all of this. I don't need it. Results DL, that was the folder I used, and just plot the solution, the main solution for this problem. So I'm just gonna do the just the displacement field, just to look at something. So yeah, lengthen, activate, and then shorten. Again, you can look at all the video files that we have for outputs, fiber rotation, strain rates, plenty of options there. Any questions? Anything that didn't work? Anything that didn't converge? Anything that crashed? Nothing? Good. So, if you want to read more about this, well, first of all, the DL2 tutorials. I feel like that's really important to understand the way we coded things. Because in terms of like the code itself, right? So Flexodeal Lite is pretty much structured like a DL2 tutorial, right? So everything's in one code on purpose, right? In terms of mathematical details, where we have a paper out there, but there's also, let me just put this in full screen mode. There's also my thesis too, not the entire thing, of course, just only chapters 5 and 6. 5 is basically mathematical details. 6 is more documentation about Flexodeal that eventually will make it to its separate webpage. We have to still have to set that CI/CD framework. Then PowerView. Again, PowerView is a really powerful software. You should learn it on its own, and then when you combine two things together, you can really create cool visualizations, right? So yeah, that's about it. Follow us on GitHub, LinkedIn. Again, this software has been created for, it's a work of many people throughout many years, all of them here. Some of these members are present, some others former members too. So thank you to all. Again, if you have any questions, like feel free to email me. We'll be in touch.